Good afternoon, everybody, and welcome to another ASCE live stream. My name is Brad Keeler. I'm the director of the Geo Institute at ASCE and your guide, shepherd for ASCE conferences. We're excited to start a three-part series today of live streams, previews of stuff that you will see. Well, not exactly like it, but we're going to do Seattle case histories because ASCE convention, in case you haven't been paying attention, is coming up in October in Seattle. So, of course, we thought, what better way to get you prepared than to give you some of the flavor of some local civil engineering projects. So over the next couple of months, that is exactly what you will be getting. Today, we have the presentation on Rainier Tower. We will be announcing our July and August presentations very shortly, and you will want to come back to check those out as well. If you don't know anything about ASCE, well, first of all, congratulations for being here. Second, it is a membership society, the largest in the world for civil engineers, with over 160,000 members. We have specialty institutes, we have amazing advocacy programs, continuing education, and a lot more. After you watch this today, you should head over to asce.org and find out more, where you can also get more information about the ASCE convention, including reasons why you may want to attend. If you like what you see today, and I think you will, you should also click like, subscribe, and get notifications. If you do those things, we will let you know every time we post something to the YouTube channel. With those things out of the way, your moderator today is the chair of the aforementioned ASCE Convention 2025 in Seattle, Washington, October 8th through 11th. It is Michelle Madzalin. Michelle, welcome and thank you for doing this today.
Sure. Nice to be here. I am Michelle Madzalin. I am a senior transportation manager at ELA Group in Ephrata, Pennsylvania. And as Brad said, I am the chair. So I am really excited to talk about the convention. There are several reasons you should be there. There are technical issues as well as networking opportunities. We cover things like artificial intelligence, emerging technologies, history and heritage, integrated systems, significant projects, industry standards, and public policy. So there's a lot of great technical information that you can gain. Now it is my pleasure to introduce the speaker. His name is Ron Klemenczyk. He is the chairman and CEO of Magnuson Klemenczyk Associates, a leading structural engineering and civil engineering firm based in Seattle. He has been recognized globally for innovation of high-rise designs, and he is known for delivering creative, cost-effective solutions through the visionary big picture approach. So I would like to turn it over to Ron to talk about the Rainier Square.
Thanks, Michelle. Really appreciate that. And thanks, Brad. First, before I jump into the presentation, I want to offer my personal warm welcome and invitation for you to join us in Seattle. It's a beautiful, beautiful place on the planet Earth. Northwest corner of the U.S., mountains, water, forests, lots of beautiful things to see, lots of great outdoor activities to do, a wonderful public market, wonderful art, etc. So I hope you'll join us in Seattle. I'll be there to welcome you personally. One of the things you'll see in Seattle is the building we're going to talk about today, Rainier Square. But one simple reminder, if you come to Seattle in October, do bring your rain gear because it rains. All right, I'm going to now share my screen. Bear with me. There we go. Brad or Michelle, are you able to see my screen?
Looks fantastic.
Great. All right, thank you. Off we go. Rainier Square is the second tallest building in Seattle, newly minted and fresh on the Skyline. And we're going to talk specifically today about a new structural system called SpeedCore and why it's a game changer. Here's the building after it's been completed. It's situated right next door to another very famous Seattle landmark, Rainier Square, which you see on the left, was designed by the famous architect Minoru Yamasaki. And Yamasaki designed many famous buildings around the world, most notably the World Trade Center towers in New York City. But this particular building was one of his early 1980s projects, and it's actually the headquarters for our offices in Seattle. If you'd like to pay us a visit, we'd welcome you. We're on level 32 in Rainier Tower. Rainier Square is the building we're going to talk about, which is the building on the right, second tallest building in Seattle. It opened about 3 years ago now. When we first conceived of the design of Rainier Square, we took a pretty traditional approach with a reinforced concrete core and steel framing surrounding it. And it's a tried and true method we had executed on many buildings around the world, and not just we, MKA, but we, the structural engineering profession, designs many, many buildings in that way. About halfway through the project, our client challenged us to come up with a better, faster, cheaper idea. So we came up with this idea of employing SpeedCore, which was a system never done before, never executed on a building before, especially at this scale. And Engineering News Record got wind of that, and they wrote this very interesting article about new technology adoption in the AEC space and how reluctant we all are maybe to adopt those things, entitled Calculated Risks. The participants in this project, our client, ultimate client, was Wright Runstead, the developer, who is a very prolific, highly regarded developer in Seattle. They've done many, many of Seattle's best buildings. NBBJ was the architect, and of course, we were the engineers, Lee Crutcher Lewis, the contractor. Here's some of the stats about the building. What you'll note about the image on the right is it's a very slender tower, 850 feet tall, and what's really not shown clearly in this image is we have, in addition, 7 levels below grade for 1,000 parking stalls. So it's a very, very massive building, taking up about 3/4 of a city block in downtown Seattle. As I mentioned, the structural design was originally conceived as a reinforced concrete core. Here you see it colored in red. A very traditional core arrangement, the core in this case being 40 feet wide and 90 feet long, so 3 40 by 30 cells at its base. And as the tower goes up, the tower footprint gets smaller, and so also shrinks the core. Midway up the building, we're at 40 feet by 60 feet. And at the very top of the building, where there are residential apartments, the core is reduced down to 40 feet by 30 feet. That's a very traditional layout for a structural bracing system for a tower of this height. But in addition, because of its slenderness, this tower also required a series of outrigger trusses and belt trusses that were located at a mechanical floor about 2/3 of the way up the building. In the case of Rainier Square, this mechanical floor delineated the differentiation between the office uses below and the residential uses above. So it was a very convenient place to locate these outriggers. And that was the system that was originally conceived. As I mentioned, this is how we've designed and built buildings for the last several decades. Reinforced concrete cores, steel floor framing, tried and true method. What you'll note in this particular image is that the reinforced concrete core is out well ahead of where the steel erection is occurring. And the reason that's the case is that the cycle time to build one floor of the reinforced concrete core is about 1 week, whereas the cycle time to erect the steel floor framing is as fast as 3 to 4 floors per week. So the steel would overtake the reinforced concrete core very rapidly if the core is not well ahead of the steel erection. This was, in effect, the problem statement for us as we imagined another way to design and build the building. How can we squeeze this time lag out of the construction process? In the case of Rainier Square, that time lag was substantial, measured in months. Complicating it further was this mid-height mechanical floors with the outrigger trusses and belt trusses. The connectivity between those trusses back to that reinforced concrete core wall is very complicated, requiring very huge embedded steel shapes within the reinforced concrete, making that portion of the construction very laborious, very costly, and slowing things down tremendously just at the 2/3 height of the building. So it was a further complicating factor. That's where we introduced the idea of what was then called a concrete-filled composite plate shear wall, CFCPSW for short. Now, as AISC has named it, speed core. But essentially it's a panelized, prefabricated steel sandwich panel that's prefabricated in a shop, trucked to the site, erected like giant Lego blocks, and then infilled with concrete in a trailing operation. A typical panel looks something like this, where it's 1 story tall, in the case of Rainier Square, that being 14 feet, and 1 bay long, in the case of Rainier Square, 30 feet to 40 feet long. So a typical rectangular panel looks something like this. All the dots that you see on the face of the steel plate are cross tie rods that interconnect the 2 steel face plates, and they serve many, many purposes, the cross tie rods. They serve first as the stability for the prefabricated panel. Next, they resist the hydrostatic pressure of the concrete that is placed inside. Thirdly, they invoke composite action between the steel and the concrete. And lastly, they provide a confining pressure for the concrete under compression. So these cross tie rods are very important to the overall system. There was a second type of typical panel we called the dog bone panel, or an H-shaped panel, in which case typical coupling beams or link beams were also prefabricated in the shop to make these panels easily erected and to keep the detailed fabrication and assembly of the link beams in the shop and out of the field. So that helped, again, speed along construction. Of the many details involved in this system, there are 2 that are really most critical. First being these cross tie rods I mentioned and their connectivity to the steel plate. What you see on the screen now on the left-hand side are 3 different options on how one might consider connecting those cross tie rods to the steel plate. On the leftmost, a double nut. On the center, a inside fillet weld with a double nut on the opposite face. Or on the third case, an inside fillet weld and a plug weld. On the right-hand image, you see the rods protruding through this face plate and an outside fillet weld applied to connect the rods. All 4 of these methods are satisfying the engineering requirements and can be designed appropriately. The question for the fabricators was, which one of these do you prefer? Because at the end of the day, in Rainier Square, there were 240,000 cross tie rods, meaning there were 480,000 connections to make. And even if you save 15 seconds per connection times 480,000, it's a big number. Ultimately, the fabricator chose the connection on the right, where the face plates are drilled, the rods pass through the face plates, and then are welded with a fillet weld on the outside face. The other detail that's really critical in thinking about this assembly is shown best in the right-hand image, and this is the lower panel and upper panel are connected in the field, in this case with a weld, a multi-pass weld, which is in this case a partial penetration weld with a reinforcing fillet. The design criteria for this weld was to develop the full tensile strength of the plate so that we were dealing with seismic forces and wanted to ensure that the connection itself was not the point of failure, but that any failure would be pushed into the plate itself. And so this is what was employed on the project. We did provide the steel erector with a choice here. This is a system that you are able to bolt the field splices from panel to panel or weld, and that choice was given to the erector. In the case of Rainier Square, the erector elected to go with welding, mainly due to the fact that they thought that they'd have more flexibility and easier time with fit up in the field. Those are the two most critical details. There are plenty of others to think about. The erector was key in plotting out the strategy to put this together, and the erector brought to the table the idea of prefabricating corner columns, box shapes, if you will, that were 2 stories tall, because erecting 2-story tall box columns is something that they've commonly done. They feel they can handle them readily, can plumb and true them easily, and then use those 8 box columns as a framework, if you will, to fly the very large wall panels in and then use them more as a template. And so this was the strategy developed by the fabricator, which then we employed in the design. Here's a bit of how it looks as it goes together. The 8 box columns you see, and then the different panel types, both with and without the coupling beams, the red colored pieces being those coupling beams. The coupling beams in this image look like they're in an odd location, but if you can imagine, they are in the typical location at the head of a wall opening. And it's that the field splice then was located approximately 4 feet above the top of deck, making it very easy for the steel erectors to make that field splice at hip height as opposed to overhead or at foot level. I'll back up a step or two. About 10 years before we started the design of Rainier Square, a research project was undertaken, led by Purdue University, but funded by the Charles Pankow Foundation and the Magnuson Klemensic Associates Foundation. And we first started working with Professors Bowman and Krager in the Bowen Lab at Purdue University to test this assembly of prefabricated panels under a variety of loading conditions. In the case here in this image, you see a 5-story tall T-shaped section filled with concrete that was then tested for seismic loading. But we went through a whole series of tests, not only of the concreted panels for seismic loading, but in this case, an unconcreted panel, seeking to understand the question, or the answer to the question of how much load can we put on this panel before we must put concrete in it. The idea was to erect the panels quickly, speeding construction along as rapidly as possible, and only place the concrete inside of it when it was necessary. So understanding how much temporary load these panels could take was very critical in terms of realizing the time savings. Here you see, if you're looking carefully, that the wall panel has actually buckled, and that was the point of this test, to understand when do we achieve or initiate buckling in the wall panel due to applied load. And that sets some limits then on the design of the panel and how far behind the concreting operation can trail. A few years later, we extended our research work at Purdue University with Amit Varma and his team of researchers, looking at a variety of other details of this assembly, in this case, looking at a variety of ways to connect the cross tie rods and exactly what are those cross ties made out of. Are they in fact cross ties? Are they headed studs, or some combination thereof? So we tested numerous configurations of panel assemblies. In parallel, we had a separate team going at SUNY Buffalo, led by Michel Brunel and his team, looking at a variety of other conditions on these wall panels. In the background, again, you see a T-shaped wall that was subjected to biaxial bending. In addition, Michel Bruneau's team at Buffalo tested bolted field splices. Here you see kind of leaning on its side, a T-shaped section with bolted splices. So we were testing also the ability to bolt these splices in addition to welding the splices to prove out a variety of bolting methods. Complementing all of this in-laboratory research that we started some 10 years before we actually designed Rainier Square, when we got to Rainier Square and the design of it, we felt, who's we, the owner, the constructors, the erectors, all the project participants felt it would be really useful to build a full-scale mock-up of a portion of the core to understand how to go about building it prior to actually game time, if you will. So here you see a mock-up full scale of a portion of the core made of wood formwork with plastic cross ties made of PVC actually, mimicking the geometry of the wall section. But the primary purpose of this mock-up and these tests were to understand the performance of the concrete mix design that we had been experimenting with. We wanted a mix that was easily pumpable, easily placeable, and that flowed around the section so that we only needed to place the concrete in a limited number of placement ports. After the concreting operation in this mock-up, we were able to strip the wooden formwork away from the concrete to make sure that we had adequate coverage, that there wasn't serious segregation or cavitation anywhere, and we're pleased to find that the concrete mix design performed very, very well. In addition, in this mock-up, we did all of the normal engineering tests, inclusive of compressive strength, modulus of elasticity, heat of hydration, shrinkage, etc., to make sure we understood all of the properties of this particular mix and how it would perform in the wall section. In addition to the concrete mock-up, a full-scale steel mock-up was also built of a corner of the core. That mock-up was built, as were all the panels, built in a shop in Portland, Oregon. Here you see one of the full-scale corner columns being fabricated. The Swiss cheese holes that you see in the left-hand plate are flow holes to allow the concrete to flow inside the wall and around the corner. You also see a good image of the cross tie rods in those 4-foot square box columns. All of the modules were put on a truck in Portland, shipped up to Seattle. In this case, you see inclusive of some mechanical penetrations that were prefabricated into the wall panels. And then the erection team had a chance to practice. This was off in a yard in Seattle where the erection team was able to experiment with how do we pick these very large panels off the truck. They weighed in the range of 9 to 10 tons each. How do we handle them in the wind? How do we move them into place? And then ultimately, how do we lower them down and get them plumb and true in the field? You get a pretty good feel for the scale of this operation with the people standing in the foreground, that these panels are quite massive, inclusive of the corner columns, but handling them actually went very, very well. A number of lessons were learned through both the concrete mock-up and this steel mock-up. For example, in the next image, it'll be more clear. Here you see a field splice that's yet to be welded. And of note here, you'll see that the cross tie rods are shown equidistant above and below that splice. What we learned from this mock-up was that a better strategy may in fact be to offset that from equal to 25%, 75% on the spacing. The reason being is that with that longer tongue on one end, in our case, it ended up being the upper panel, the longer free edge of the plate, if you will, allowed greater flexibility and adjustment in the field for the plate-to-plate splice. as opposed to the equal spacing of the cross ties you see here. It was a very seemingly small adjustment, but very, very important to enabling the erectors to achieve the speed and the field fit up that they hoped for. Also, in this image, again, back to the field splice, we experimented with semi-automated welding. I stopped short of calling it robotic welding because it really wasn't a robot, but it was an automated welder, and also hand welding. And what was learned from that experiment was that the automated welding in the field doesn't do well. There are two issues primarily. One was the fit up from plate to plate with the introduction of all the cross tie rods and the heat associated with welding those cross tie rods. A very small amount of wobble was introduced into the plates, causing them to not be 100% precisely aligned in the field. And so that wobble was not something the automatic welding machine was very happy about, whereas the hand welding was easily able to adapt to the 1/16 of an inch out of alignment, sometimes even as much as 1/8 of an inch out of alignment. The hand welding was able to deal with that readily. So at the end of the day, the entire project was hand welded. Interestingly, perhaps, there's 32 miles of hand welding in Rainier Square. But given the way the project was built and sequenced, that hand welding was never on the critical path. After all of this testing in the laboratory and experimentation with mock-ups, it was kind of game time, if you will. And here we started the shop drawing process. And it was a typical shop drawing process, detailing out all of the various panels. Here you see, once again, a typical rectangular panel, nominally 14 feet tall, nominally 30 to 40 feet long, inclusive in this case of a large penetration for a mechanical duct. Also inclusive of, you see, the deck ledger angle for the incoming metal deck that would be supported by the wall, and the shear tabs for the incoming steel beams that would be connected to the wall. All of those pieces were shop fabricated such that when this panel was erected in the field, it was ready to receive anything and everything that was attached to it. Similarly, the H-shaped panels went through a similar process, prefabricating the link beams in the shop and getting ready for concreting in the field. But once again, you see the deck ledger angle, the shear tabs in place, as well as the upper plates and side plates for the link beams. In some of these images, here you can see it very faintly, I suppose, in between the panels, in addition to the cross ties. You see the hints of a few diagonal members. In the larger panels that were nearly 3.5 feet in width, the erectors and fabricators felt that some supplemental trussing or supplemental bracing inside of the panel for handling an erection was critical. So that was added into the panel fabrication, not really part of the structural design, more so to stabilize the panel during fabrication, shipping, and erection. Ultimately, the panels showed up on site. Here you see the first load of panels arriving on site. I had the kind of personal vantage point of looking out my office window on the 32nd floor every day, down into the hole, into the site, and seeing these sites. So this particular photograph was actually taken from my desk. So it was a unique opportunity to actually witness one of our designs every day right outside my window. So here's the lower panels being lowered into the hole and the connection to the foundation. The connection to the foundation in this case was a source of great discussion with the contractors, the fabricators, the erectors, and the rebar placers. The foundation in this building is a mat foundation, 12 feet thick, We have very good bearing in downtown Seattle, so we don't require piling for most of our buildings in downtown. Most of them sit on shallow foundations or mat foundations. And the question was how to connect this set of wall panels to that mat foundation. In the end of the day for Rainier Square, the detail that was adopted you see here, where stanchions or columns were placed along with the first lift of wall panel, and all of that assembly was made true and plumb and very, very precise, noting that we wanted to make sure that was all situated in exactly the right location as we launched the rest of the wall construction going upwards. So this operation was handled with great precision, with lasers to ensure that it was in the right position before the rebar was completed for the upper layers of the mat and before the mat concreting was completed. After the mat concreting was completed, we're ready to go. And here you see a shot looking down once again from my office at kind of day one of steel erection. We've got the mat poured, the starting blocks for the speed core wall are in place, and we're ready to begin steel erection. As a side note, originally this building I mentioned early on, we have 7 basements for parking, a very deep excavation, 100 feet deep in fact. Originally the design of the basements was considered as a reinforced concrete structure. When we switched to the speed core system, that decision was reevaluated and ultimately changed the design of the below grade structure from reinforced concrete to structural steel. The additional excavation for the required added floor to floor height was offset and then some by the speed of erection coming out of the hole. So there was an evaluation done of that, and at the end of the day, the decision was made to move forward with steel erection starting off the top of the mat, inclusive of the below grade garage. This image gives you a good idea of how the erection proceeded. You see the 2-story tall box column standing up. You see some of the wall panels inserted, and if you look closely in the corner column, both at its base and then a couple of times up its height, you see a circular hole. That is a placing port into which the concrete pump was inserted to place the concrete. There was a placing port located in each of the 8 corner columns, allowing us to insert the pump and present concrete into the wall assembly at each of the 8 locations, and then allow it to flow through the remainder of the wall. It proved to be a very successful strategy. The concrete was placed 1 floor at a time in a downward fashion, so the concrete was allowed to free fall 14 feet. But this was, again, something that we proved to be fine in our mock-up, noting that the ultimate mix design that we used in this project did not include any coarse aggregate. It only included sand, cement, water, and some admixtures. It was more of a grout than a concrete. And that prevented the segregation question from being a particularly worrisome issue. Up went the erection. We're getting close to level with my personal office. You can see how quickly or how closely the core wall and the steel erection are aligned with one another, comparing that to the image I showed earlier, where the reinforced concrete core was well ahead of the rest of the steel erection. This allowed the steel erection team to work very rapidly. At the peak of the speed on this project, they are erecting 4 floors per week. So it was a very, very rapid erection once we got up, in particular to the upper portions of the building with a smaller core and a smaller floor. A close-up of the core, once again you see the placing ports where the concrete would be inserted. If you look very, very closely at the tops of the link beams, you'll see a small hole there as well. That was, we'll call it a blow hole, but the idea there was to enable us to ensure that we had full coverage or fully filled link beams, when we knew the concrete was coming out of the top of the link beam through those holes, that we knew we had kind of placed enough concrete inside of the overall wall section and that the link beam was indeed full of concrete. Also shop fabricated were the steel connections for the outriggers. This saved a tremendous amount of time and field headaches, not having to do that work in the field as it would be done typically in a reinforced concrete building. So all of these very complex, very heavy connections between the core walls and the outrigger trusses was all made in the shop. In addition, connecting to the outrigger columns that you see here on the right-hand side of this image were also prefabricated, the connections and the columns themselves. I should mention that the outrigger columns were in fact made of the same type of construction. They were 5 feet by 5 feet square. You see the cross tie rods protruding through, so they were 1/2 inch thick steel plate, 5 feet by 5 feet square in plan, with cross tie rods spaced at 12 inches on center in a field in both directions. This gives you an idea of what the outriggers looked like when they were completed. Very heavy sections in the case of the outriggers themselves. The green shapes you see to the left were double wide flange sections, and the gray section you see to the right is a buckling restrained brace. And the buckling restrained brace was used as a fuse for the overall seismic system so that we could control the amount of axial load that ultimately was delivered to the perimeter columns. 10 months to the day that we started steel erection at the top of the mat to the day that we placed the final roof beam on the top of the building, the topping out party, if you will, was exactly 10 months to the day. So from basement -7 to the top of the building, the uppermost occupied floor is level 58. The roof is level 59. So 59 and 7, 66. 66 floors of steel construction erected in their entirety for the topping out ceremony in just 10 months. Very, very rapid. You see also notably in this slide that much of the skin is on the building as well while we're topping out the steel at the roof. Here we're going to see a brief time-lapse video that shows first the excavation being dug 100 feet deep and a very precarious Rainier Square sitting next to it. I had several months of anxiety as that hole was laid open. And then up went the building very rapidly. The time-lapse photography we had on the building across the street, thankfully, is all time-stamped, so we know precisely how long this took to build. It's a good record of what was accomplished. From an overall construction point of view, the building was originally scheduled to take 32 months to complete. That was with the reinforced concrete core, kind of the traditional design. The building itself was actually completed in 22 months, a savings of 10 months on the overall schedule of the building, which for the client was a wonderful outcome, because not only does that save them a tremendous amount of money in contractors' general conditions and interest on their loans, their construction loans, but it also allows them to start charging rent 10 months sooner. So it was a huge win for the client as well. As I mentioned, the building has been open and occupied now for a couple of years. It's a very beautiful building on the Seattle Skyline. As I mentioned, the second tallest building, the first tallest building you see off to the left, which is Columbia Center. That was built in the 1980s. So this is the brand new addition to the Seattle Skyline. And it's a wonderfully beautiful project that has all kinds of different qualities and colors to it throughout the day as the sun reflects off the very uniquely designed skin that MBBJ designed. So anyways, I invite you to come and tour the building. In the main lobby of the building, some of the speed core panels have been left exposed, and there's a small plaque that is kind of a tribute to the iron workers who worked on the building as an art installation, if you will. So most people, casual observers, come through and they think it's a piece of art, but to engineers who come through who know better and what it is, it's kind of fascinating to see that, in fact, the speed core is fully exposed. You can walk up, you can touch it, you can see it in real live living color. So you're welcome to come and look at it. It's in the main lobby of the building. And with that, I think I'll wrap it up and open things for questions. I think back to you, Brad.
I will just say if there are any questions, please type them into the chat, the question and answers. I have a question for you, Ron. Can you please tell me about the fire protection that was incorporated in the building?
Excellent question. I didn't talk about that in the presentation, and it is a very important detail. So because this project was going to be the first speed core project ever realized, we, the owner, the architects, the engineers, the team, elected to, shall we say, choose which battles we were going to fight. And the battle we wanted to fight and win was to convince the building officials that this system was legitimate, that it should be approved, and that they should give us a building permit to build the building. And the focus was on the structural design and performance of the building. That said, we elected in the beginning to take on the fire protection in our proposal to the city, saying that it was going to be fully sprayed with monocoat, that it would be fully protected, as is the rest of the steel in the building, with a spray-on fire protection. And that's what was approved, that's what was permitted. And at the time when this occurred, we didn't have any research to tell us that it could be done otherwise. Despite our intuition saying that maybe it could, we didn't really have the research to do it. As the project started to move forward after we had it approved, we went back to the city and made a second argument that said that inside the core itself, where we essentially don't have any flammable materials, we have elevator shafts and stairwells. In those locations, since there are no flammable materials and essentially elevator shafts, would you allow the elimination of the fireproofing inside the elevator shafts, for example? And ultimately, after some study and discussion, they did approve that. So what was formerly built with Rainier Square was that the outsides of the walls are fully sprayed with a monocoat fire protection system, and the inside of the core walls, in particular in the elevator shafts, are left bare. Since we completed Rainier Square, or maybe said differently, as we were completing Rainier Square, we were making a list of a number of questions and challenges and improvements that we hope to make going forward, one of them being fire. And so toward the end of Rainier Square construction, we were able to launch a research project in which we actually did fire testing, once again at Purdue University, of various speed core wall panel assemblies. Today, there exists a research report and guidance on how to go about designing the speed core walls considering fire. We've since now used that report to realize another building in San Jose, California, in which the building official presented with that research was agreeable to allowing us to eliminate the fireproofing on the inside and the outside of the core wall panels themselves. So we've advanced it to kind of the next step at this stage, where there is research, there is guidance, there's a report that allows engineers, gives engineers the right information as to how to go about designing the wall panels if you want to eliminate the wall protection itself, which we've done in San Jose.
Thank you. Can you tell me about the embodied carbon of the design?
Good question. So these days, embodied carbon is on the minds of many. as we all grapple with global warming and what we as a structural engineering community can do. Of course, building construction is a big contributor to global warming, and embodied carbon is the culprit of that. Much of that embodied carbon comes from concrete, but some of it also comes from steel. And so the question really is, comparatively, this system as compared to what we might normally build, a reinforced concrete core, is it better or is it worse? Qualitatively, we can say it's significantly better. And the evidence of that is, well, we saved 10 months of construction. So just the fact that we don't have construction activities going on for 10 more months is a tremendous amount of carbon saved. Secondly, the steel that was used in the project was sourced from locations where the steel was made using recycled materials in electric arc furnaces. And so there's a strategy there to reduce the carbon footprint of the steel itself, once again, as compared to reinforced concrete. While I can quote a number of other, I'll call them qualitative aspects of the carbon story, the truth is today, there is not yet a quantitative assessment of this versus a normal reinforced concrete core, primarily because the data associated with a reinforced concrete core construction does not exist. Specifically, what does not exist is the amount of carbon related to the formwork systems, the amount of carbon related to the embed plates that are oftentimes misplaced and need to be reworked, the carbon related to schedule. All of these things are unknowns at this moment. And so I can say qualitatively, we can make a strong case for why it's a more efficient and more carbon-friendly system as compared to normal construction. But truthfully and factually, quantitatively, the data doesn't exist.
Thank you. I have a question from Ava Lerner-Liam. I am wondering if the project team considered a network-tied sheet wall reinforcement approach to compare with the cost, performance, and resilience of the rectilinear reinforcement approach taken.
Wow, that's a very interesting question. Thanks, Eva. Hello out there. The truthful answer is no, that was not compared. In fact, I'm not sure that I completely have a clear image of what you're trying to describe. So maybe you and I will have an offline conversation at some point about what exactly it is you're thinking of, because it might be very interesting. That said, one of the ambitions with this particular system was to eliminate any and all reinforcing steel, which is what we achieved. There's no reinforcing steel at all. It's merely the steel plates that serve both as the shear reinforcing, the tensile reinforcing, and the confinement reinforcing for the concrete. By doing that, it also helped speed along construction because now we're only dealing with a single trade in erecting the building vertically. Typically, on most buildings, we're mixing trades where we have the concrete team and the steel team, and oftentimes they're fighting over who has access to the tower crane. In this case of Rainier Square, that conflict was eliminated because it was all under the control of one subcontractor, the steel erector, and the concreting operation was a trailing operation. So I know that probably doesn't answer your question exactly and directly, but I'm not sure that I can without maybe seeing a picture of what you're thinking about. So you and I will take that up offline. Thank you, though.
I have a question from a Paul Hobson. Did the faster than expected construction create any management challenges, such as outpacing material supply chains?
So yeah, also excellent question. Fortunately, our team, the contractors in particular, did an excellent job in planning. So the simple answer to your question is no, there weren't any supply chain issues. It was a very, very rigorously choreographed dance, if you will, because in particular the speed core panels were being fabricated in Portland, and it's about, without traffic, a good 3.5 hours drive by truck from Portland to Seattle. And noting we're building this building in downtown Seattle, there are truck restrictions on hours of operation in downtown Seattle. So the trucks had to arrive and be gone in a very, very small window of numbers of hours in the early morning each day. And this needed to be coordinated each and every day so that the right panel showed up at the right time and the right day, and they could keep moving along. Fortunately, in addition, the contractor did a wonderful job planning out the exterior wall installation, because that can typically be a snag in the overall erection of the building. But they did a really fantastic job in planning that out. Though one of the hundreds of lessons we learned on this project, which has inspired some new thinking, but one of the lessons we learned is that the speed core was so easy and so fast to erect that what then became the critical path work item was the installation of the horizontal deck. Specifically, the detailing of that deck, meaning the deck edge plate, the welded studs to create the composite action with the beams, the reinforcing steel that needed to be placed in the deck, all the deck detailing, and then the concreting operation. That whole sequence of events became the critical path work item for the structure. In fact, at the kind of during the project, they had two erection gangs. They had an erection gang whose sole job was to erect the core, and they had a separate team erecting the floors and detailing the floors. The core team worked 4 days a week, 10 hours a day. The horizontal team worked 6 days a week, 10 hours a day to try to keep up. And they barely caught up, or they barely kept up. And that's where the kind of friction in the system was. We could have actually gone faster if, in fact, we had a different, better strategy on how to build the horizontal work.
Again, if anybody has questions, please type them in the chat. I do have another question. With a building this tall, could you talk about the wind design that was incorporated?
Sure. Surprisingly, noting that we're in Seattle and earthquakes are kind of the thing that we think about most often. In fact, the earthquake that can be generated in Seattle due to the fault of Juan de Fuca is many times greater than the earthquake that can be generated by the San Andreas Fault in California. So the earthquake hazard is very, very significant in Seattle. That said, this building, because of its size, shape, and slenderness, wind actually controlled the design. For those of you that are aware of high-rise building structural design, we were subjected to something that's called vortex shedding, and it's a product of the slenderness and shape of the building and its orientation in the wind environment. And those kind of critical elements all came together in this case, such that the wind demands on the building actually exceeded the seismic demands. So designing the building for those forces made it much easier actually to deal with the seismic demands. However, the complicating factor was that because of this high wind response, what did enter the picture was the comfort of the residential occupants in the top of the building. On a windy day, we didn't want them getting seasick, if you will. So what was ultimately incorporated into the project is a tuned liquid mass damper on the roof of the building in order to manage the sway of the tower in high winds to make sure that all of the occupants in the apartments at the top of the building remain comfortable and aren't getting nauseous.
I did get another question in. Can you please expand upon the earthquake resilience of the building?
So this building, as many high-rise buildings are these days, but this building in particular was designed using a performance-based seismic design methodology, wherein we set aside kind of the prescriptive requirements of the code and instead had a site-specific hazard assessment done by a seismologist that defined the hazards on this site. We targeted from a overall safety point of view, a 2,500-year return period event for a risk category 3 building. And then we proved out through a rigorous analysis of 11 different ground motions that the numerical model of the building was subjected to, that the building achieved all of our acceptance criteria when subjected to these 11 different earthquakes, all calibrated to a 2,500-year return period event. And that was the design criteria for the building. We also proved out that the building could respond appropriately in smaller earthquakes, a service level earthquake, if you will, an earthquake that happens one time every 50 years, for example. But from the earthquake design point of view, the controlling demand, if you will, was the 2,500-year event that was considered.
Can you go through some of the lessons learned and something that could be used on future projects?
Sure. We don't have enough time to go through all of them. Literally, there's probably 100 lessons learned. I would say one of the most important things to just be aware of, the success of Rainier Square and the success of 200 Park in San Jose was made wholly possible by the early participation of the general contractor, the erector, and the fabricator in the design process. And by working with them collaboratively throughout the design process, we were able to collectively come up with strategies, everything from the connection of the foundation to how do we connect the cross ties to the wall panels, to you name it. Every last detail was sorted out on both of those projects with the contracting team participating in the design. It was hugely important, hugely beneficial. So if you're going to attempt one of these buildings, which I would encourage you to do, lobby your client to have them engage their favorite contractors and erectors and have them work with you together, and you'll be well served. There's countless other little technical details we could talk about, but I'll save those for another day.
Okay. I think Brad is going to come on, and I think we're going to wrap up. Really appreciate your time and great presentation. Thank you, Ron.
Thanks.
That was fantastic. And as I told you yesterday, Ron, when we went through it for the tech test, I like the ones that are more case history style with a lot of photos. That was fantastic. It was easy to follow, and I hope everybody out there liked it too. For our viewers, thanks for being with us today. Thanks especially to those who asked questions and shared comments in the chat. We really do appreciate it. Our next live stream, we're very excited to announce, it'll be July 23rd, and we'll have two presenters from Shannon and Wilson on this one. It's going to be on the Dungeness Levee project and a Puget Sound restoration project. So as you can see, we are going to be hitting all the different aspects of civil engineering. Well, a lot of them. I won't say all. That might be a little bit of a stretch. But a lot of the different aspects of civil engineering as we get through these sneak previews of ASCE convention, which again, after you get done watching this today, head over to convention.asce.org to get more information about the conference and to register. If your company would like to exhibit or sponsor, we still have opportunities available for that as well. We would love to see you there and help you get those eyeballs on your firm. One more thing, again, we're at the end. Click like, subscribe, get notifications. We'll let you know again every time we post something to the YouTube channel. Don't forget, July 23rd, next live stream, October 8th, start of the conference. Ron, thanks for doing a great job presenting today. Enjoyed it. Michelle, fantastic job moderating. Good luck as you barrel towards the event as the chair. And Amber Davis was our producer today, and we will see everybody soon with another ASCE live stream.